The permit was signed, the tank looked empty, the gas test was recorded, the welder struck the arc. Then one spark found what everyone missed.
I mean, it is just the ultimate nightmare scenario in process safety. You follow the administrative rules, you check the boxes, you sign the forms, and then the environment still turns lethal in a fraction of a second.
Welcome to Key Safety Talks. Today, we are taking a special deep dive into a topic that honestly keeps safety professionals, facility managers, and just frontline workers awake at night.
Yeah, it really does.
We have a massive stack of sources in front of us today. We're looking at investigation reports from the U.S. Chemical Safety Board, the CSB, detailed OSHA standards, like 1910.252 for welding, 1910.146 for confined spaces, and 1910.134 for respiratory protection.
Right, the core standards.
Exactly. Plus, we are looking at some truly harrowing real-world case studies to try and bridge that gap between regulatory theory and, well, fatal reality. So what's our mission for this deep dive today?
So the mission today is to really deconstruct exactly why routine hot work goes catastrophically and often fatally wrong. We want to examine that dangerous illusion of safety that gets created when highly complex facilities place blind trust in paperwork instead of physical engineering controls.
Okay, let's unpack this and just address the elephant in the room right away. I was reading through these CSB reports, and the amount of times a perfectly signed permit was just sitting on a desk while a facility literally blew to pieces is, it's staggering.
No, it's incredibly common.
Like, how does a piece of paper magically make an explosive environment safe? Spoiler, it doesn't. Bureaucracy does not halt ectothermic reactions. A piece of paper on a clipboard doesn't magically neutralize a flammable atmosphere. Yet, in the industry, we often treat the permit as this magical force field.
Yeah, that administrative reliance is really the foundational issue we have to dismantle today. Safety is physical execution. A signature does not change the laws of physics. It doesn't alter the vapor pressure of a hydrocarbon, and it certainly doesn't dictate how a stray spark travels.
Right.
We have to shift the operational mindset from, we have a permit, so we are safe, to a much more rigorous standard. We have to ask, what physical engineered actions have we verified in the field to ensure that the next spark doesn't ignite a disaster?
Knowing our audience, I think we all understand that welding or using an oxyacetylene torch is hot work. But looking at the fatalities in these reports, the disasters often trigger during tasks that workers don't immediately classify as high risk.
Exactly.
We're talking about like a portable grinder on a rusty pipe or using a battery-operated drill near a vent. The ignition source isn't always this massive blue flame.
No, not at all. According to OSHA and the CSB, hot work is any operation that introduces a source of ignition into an environment.
Okay.
So the regulatory definition encompasses arc welding, cutting, brazing, and soldering, of course. But it also explicitly includes grinding.
Because of the sparks.
Right, because a grinder throws off a continuous shower of hot metal filings with immense thermal mass. It includes riveting, heating a frozen line, or using any fire or spark-producing tool. If it can create a spark, a naked flame, or significant localized heat, it is hot work.
Wow.
And when you combine that energy with the geometric complexity of industrial assets, tanks, process lines, drains, sumps, and vessels, you create a highly volatile equation.
Let's talk about that geometric complexity for a second.
Yeah.
Because these assets are inherently high risk, not just because of what they hold, but literally because of how they are built. You've got baffles, intersecting pipes, hidden cavities, dead legs. They are designed to contain materials, which means they are incredibly efficient at trapping residual chemicals, sludge, and vapors, entirely shielded from ambient air circulation.
And this leads us to the trap of normal, which is perhaps the most insidious psychological hazard in process safety. Well, when a maintenance crew performs a task 99 times without incident, a profound cognitive bias sets in. They start treating the mechanical tasks, the grinding, the cutting, as the primary hazard.
Oh, like they're just worried about cutting themselves.
Exactly. They forget that the real hazard is the invisible, highly flammable vapor lurking in the microenvironment, just waiting for the hot work to interact with it. All it takes is a single piece of hot slag falling into an unsealed drain to instantly ignite that invisible fuel.
The John Capana incident from 1979 in a New Jersey refinery is a perfect, tragic illustration of this. It's just a textbook case of bad hazard communication leading to a catastrophic assumption.
It is a profound example. And unfortunately, the exact same systemic failures that happened in 1979 are still showing up in CSB reports today.
Yeah, so for those who might not remember the specifics of the Capana case, he was a 20-year-old contract worker. His crew was called back to the refinery to dismantle an old pumping station. The crucial detail here, like the absolute failure of hazard communication, was that the facility explicitly told this crew they were working on a water pumping station.
Right. They were handed a conceptual model of the plant that did not match the physical reality. In process safety, when your management of change your MOC fails to accurately track what material is actually flowing through legacy pipes, you are setting up your frontline workers to die.
So they get to work trying to dismantle the pump, starting with the flange bolts. But the equipment is old, the bolts are severely corroded, they're torquing on them, busting their knuckles, and the metal just won't budge. So they pivot to a very standard, routine workaround. They decide to use an acetylene torch to cut the bolts off.
Which, under their false assumption, makes sense.
Exactly. In their minds, working on a water line, applying localized heat is a totally rational engineering decision.
But physics doesn't care about their assumption. The tragic reality was that this was not a water line, it was a crude oil line. And crude oil contains a spectrum of volatile organic compounds.
And the moment that flange separated, the moment the physical integrity of that pipe was broken while the heat of an acetylene torch was present, it detonated.
Yeah.
Capana survived, but just barely. He was burned over 90% of his body, enduring over 75 surgeries in the 3 decades following that accident.
And Mr. Capana spent years after his recovery advocating for process safety, explicitly warning operators and contractors not to fall into the trap of assuming a PORP line is what someone says it is, verbal information, or even an outdated P&ID. A piping and instrumentation diagram is not physical verification.
So what does this all mean for the worker? I mean, it sounds like treating hot work as routine maintenance is like driving a bomb to the grocery store and assuming it's safe just because you take that route every day.
That's a great analogy. It highlights a fatal assumption about what is inside the pipes, which leads directly to one of the most dangerous myths in industrial safety, the empty tank. I will state this as clearly as possible. Empty tank does not mean vapor-free tank.
Right, because empty usually just means pumped out.
Exactly. When an operator says a tank, drum, or container is empty, they usually mean the bulk liquid product has been pumped out down to the suction nozzle. But the physics and chemistry of industrial containers dictate otherwise. Empty equipment almost always contains residual hydrocarbons clinging to the walls, a thin film of liquid in the crevices, or a heavy layer of sludge resting at the bottom.
And people forget about vapor pressure. That residual sludge isn't just inert mass, it is actively off-gassing.
It is actively vaporizing. It releases volatile organic compounds into the headspace, the enclosed volume of the container above the residual liquid. Because the container is closed, or mostly closed, those vapors cannot disperse naturally into the atmosphere.
Because there's no wind in there.
Right. Natural ventilation is completely ineffective inside confined geometries. The vapors concentrate. They easily reach their lower explosive limit, or LEL, creating a perfectly mixed, highly flammable atmosphere inside a container that a worker mistakenly believes is entirely safe because a pump ran dry.
And the ambient environment itself can actively weaponize that tank against you. Like the weather, the temperature outside can turn a seemingly stable environment into a bomb within hours. Let's look at the Bethune Point wastewater plant tragedy in 2006.
The Bethune Point incident is a masterclass in understanding how environmental factors, specifically thermal dynamics, alter hazard profiles dynamically.
The setup was entirely routine. Clyde Jones, a 40-year-old crane operator, was just doing his job. He thought he had a safe 7 to 3:30 shift. He was operating a crane while 2 other workers were elevated in a man-lift basket. Their task was to use an oxyacetylene torch to cut and remove a steel roof positioned over some chemical storage tanks.
Now, one of those tanks was designated as empty, but the adjacent tank contained approximately 3,000 gallons of methanol. And methanol has a relatively low flash point and is highly flammable.
Right, and they were up there cutting the steel roof directly above it. But it was January in Florida. It started out chilly, but as the morning progressed, the sun rose higher and started hitting the outside of that steel methanol tank.
This is the physics of solar heating. As the ultraviolet radiation and ambient heat warmed the steel shell of the tank, that thermal energy transferred directly to the liquid methanol inside. The added heat drastically increased the vapor pressure of the methanol, causing it to evaporate at a much faster rate.
Wow.
That highly flammable methanol vapor expanded. It had to go somewhere, so it began venting straight out of the top of the tank, pushing past a corroded flame arrestor.
It vented right into the exact airspace where the workers in the man lift were showering down hot sparks from their cutting torch. The sparks found the venting methanol vapor. The fire flashed back through the compromised flame arrestor and directly into the tank itself. The entire tank detonated. Burning methanol spewed out of the shattered piping. It engulfed the workers in the basket, killing one, and the flames cascaded down, completely enveloping Clyde Jones's crane cab. He died the next day in the hospital, leaving behind a wife and a 3-year-old.
It is a devastating reality check. Hazards are not static entities. The environment changed the hazard profile of that tank hour by hour, minute by minute. A tank that might have technically been below its LEL at 6 a.m. became a venting bomb by 10:00 a.m. simply because the sun came up.
Unbelievable.
We saw the exact same mechanism at the Motiva Enterprises refinery in 2001.
Right, the Delaware City incident. In that report, workers were repairing a catwalk above a sulfuric acid tank farm. The specific tank they were working over, tank 393, was severely compromised. It had literal corrosion holes in its roof and shell.
And once again, solar heating was the catalyst. Over the course of the workday, there was a mere 14-degree Fahrenheit temperature rise. Now, this tank primarily contained waste sulfuric acid, but because of process upstream, it also contained a layer of flammable hydrocarbons floating on top of the acid.
Oh, I see.
That 14-degree ambient rise was enough thermal energy to cause those residual hydrocarbons to rapidly vaporize, pushing a massive volume of new explosive vapors out through the corrosion holes in the roof.
And at 1:30 in the afternoon, a worker's electric arc cutting system threw a spark that found that newly formed invisible vapor cloud. The explosion was so violently powerful that the entire tank collapsed on itself. It released 264,000 gallons of acid, spilling directly into the Delaware River. It injured 8 workers and killed 1 contract worker whose body was tragically never recovered.
14 degrees. That is the margin of error we're talking about. A 14-degree shift changed the atmospheric chemistry from ostensibly safe to catastrophic.
Okay, here's where it gets really interesting to me. We usually worry about oil and gas, but looking at these sources, some of the most terrifying explosions didn't involve petrochemicals at all. You're saying a tank of recycled paper or dirty water can literally digest itself into a bomb?
Yes. Anaerobic biological decomposition is one of the most overlooked and misunderstood risks in confined space entry and hot work. People look at a tank of wastewater or paper pulp or fish byproducts, and their common sense tells them it's mostly water, water doesn't burn, therefore I am safe. They fail to account for the microbiology.
Like the Packaging Corporation of America, or PCA, incident in 2008?
Precisely. This was a paper mill in Tomahawk, Wisconsin. They had an 80-foot-tall storage tank containing a thick mixture of recycled paper pulp and water. The plant employees had absolutely no idea that deep inside that tank, microbes were actively breaking down the waste cellulose fibers. This anaerobic biological decomposition process produces a tremendous amount of explosive hydrogen gas as a byproduct.
And the flammability range for hydrogen is incredibly wide, right? It can ignite at concentrations anywhere from roughly 4% all the way up to 75% in air. Plus, it's highly explosive and requires very little ignition energy.
Exactly. It requires a fraction of a millijoule to ignite. So you have a tank slowly filling its headspace with highly explosive hydrogen gas, completely undetected by anyone on site. When workers eventually performed hot work on piping connected to that tank, the sparks ignited the hidden hydrogen. The resulting massive explosion ripped the top off the tank and killed 3 workers.
It's essentially fermenting a bomb, and the CSB reports show this isn't an isolated phenomenon. It happened at Conagra Foods in 2009 as well.
Yes, at Conagra, a welding contractor was tasked with repairing a crack on the bottom of a water clarifier tank. Debris-laden wastewater had leaked through the crack and accumulated in a hidden, confined space underneath the tank's skirting. The bacterial decomposition of that trapped organic matter produced a dense pocket of flammable gas. When the welder struck his arc to fix the crack, the gas ignited. He was killed instantly.
So because these invisible hazards evolve based on temperature and biology, you can never assume an environment is safe just by looking at it. You have to test it. Which brings us to how people get testing completely wrong.
This is a critical juncture. Gas testing is not a ritual. It is risk verification.
A lot of guys treat turning on a 4-gas monitor like, crossing themselves before a long drive. They power it up, it beeps, they clip it to their belt, and they assume they are shielded by some protective aura without actually understanding the atmospheric mechanics the sensor is reading.
To understand the failures, we have to look at what OSHA Standard 1910.146 actually requires for permit-required confined spaces. The law mandates a very specific sequential procedure for atmospheric testing before anyone can enter a space, and especially before they introduce an ignition source.
Right. And most workers think you test for oxygen first simply so you don't suffocate. And while life safety is paramount, testing oxygen first is actually a critical mechanical requirement for the equipment itself, isn't it?
That is exactly right, and it is a point that is vastly misunderstood in the field. Yes, the sequential order first, oxygen second, flammable gases third. Toxic contaminants is vital. If an environment is severely oxygen deficient, a worker will asphyxiate almost instantly. But regarding the technology of the standard combustible gas meter, the reason you must verify oxygen first is physical chemistry.
Walk us through that.
Most standard LEL sensors use a catalytic bead or a Wheatstone bridge circuit. To detect flammable gas, the sensor actually has to burn a tiny sample of that gas inside the unit. In order to burn that gas, the sensor requires ambient oxygen, usually at least 10 to 15% by volume. If you drop a catalytic bead sensor into an environment that is flooded with 100% methane, displacing all the oxygen, the sensor cannot burn the methane. It will output a false zero.
Wait, really? So if a space is completely saturated with explosive gas, but oxygen deficient, the meter might literally read 0% LEL. It will tell the worker the space is perfectly safe from flammables.
Precisely. The space is actually a massive bomb waiting for oxygen and a spark. But the meter is blind to it because it doesn't have the oxygen required to perform the measurement. That is why OSHA mandates testing oxygen first. If step 1 fails, step 2 is essentially a random number generator. Only after verifying sufficient oxygen do you test for the lower explosive limit, and finally for toxic gases like hydrogen sulfide.
Let's analyze the deadly mistakes and how people actually deploy these meters in the real world. Mistake number 1 is what we call the one-and-done test.
Right. We discussed the Moteva refinery explosion earlier. The permit records show they tested the air with a combustible gas detector at 7:45 a.m. They found 0 flammables. They signed the permit, authorized the work, and they never retested. The catastrophic explosion happened at 1:30 p.m.
I mean, testing at 7 a.m. and welding at 1 p.m. is like checking yesterday's weather to decide if you need an umbrella today. It represents a total failure to grasp that industrial environments are highly dynamic.
It's exactly. The Tepe-Zygo fuel terminal explosion in 2009 was nearly identical in its systemic failure. 3 contractors were working on the internal floating roof of a gasoline storage tank. They performed atmospheric testing at 7 a.m. They worked for a few hours, went to lunch, and returned to the tank. They never retested the air after their lunch break.
Oh, no.
They fired up a cutting torch, and an internal explosion blew the top of the floating roof and the massive secondary dome-shaped lid completely off the tank. All 3 were killed. The environment changed while they were eating lunch. Continuous monitoring is the only defense.
Mistake number 2 is testing the wrong area. We talk about gas testing like the atmosphere in a tank is perfectly homogeneous, but that's not how fluid dynamics work. Gases stratify based on vapor density.
Yes. Methane is lighter than air. It will pool at the top of a vessel. Hydrogen sulfide is heavier than air. It will sink into the sumps and drains. At Conagra, with the water clarifier tank, they actually did perform gas monitoring, but they tested the general ambient area around the tank. They failed to drop the probe into the specific, immediate hidden space beneath the tank's skirting where the actual welding was taking place.
Mistake number 3 is simply not testing at all. At Bethune Point, they were cutting a roof over 3,000 gallons of methanol, and incredibly, absolutely no combustible gas testing was required by their procedures before torch work began. But mistake number 4, this is the one that forces you to question the entire foundation of a facility's safety culture: the lit torch field test.
The Partridge Raleigh oil field in Mississippi, 2006. This incident defies every principle of process safety.
3 contractors were preparing to work on an emptied oil storage tank. They wanted to check if there were any flammable hydrocarbons lingering inside. But instead of using a calibrated 4-gas monitor, they literally ignited a welding torch and stuck the open flame directly inside the tank's hatch.
The deeply flawed, fatal logic was that if there was residual gas in there, it would cause a small, manageable flash fire, effectively burning off the hazard. If there was no flash, they assumed it was safe to climb in and work.
Wait, they used the ignition source to test for the fuel? That is like lighting a match to see if your gas stove is leaking. I can't even wrap my head around that.
It is Russian roulette with industrial equipment. In this specific instance, they put the little porch in, saw no flash, and assumed the tank was safe. However, they lacked all situational awareness. They failed to realize that an adjacent tank, located just 4 feet away, still contained crude oil. As the sun warmed that adjacent tank, Vapor pressure pushed highly flammable crude oil vapors out of an uncapped pipe straight into the immediate area where they started showering welding sparks. A massive secondary explosion blew the tank lid off and killed all 3 men.
Using an ignition source to test for fuel, it just reveals an utter collapse of training. Testing must be continuous, just like monitoring the weather. But even with the best testing, the system fails if the permit to work is treated just as a bureaucratic checklist. Which brings us to the permit to work fallacy.
This is vital to understand. A hot work permit is not the control. It is proof the controls were checked.
It's the difference between looking at the blueprint of a house and actually having walls to stop the wind.
Exactly. A permit is a piece of paper. It is an administrative blueprint dictating the acceptable entry conditions, required safety equipment, and hazard isolation steps. But an administrative control cannot physically stop a chemical reaction. Contrast this with physical controls.
Like lockout tack or LO that's not just putting a do not touch sign on a switch. It physically prevents the transfer of hazardous energy.
Correct. LOTO involves placing a physical padlock through the mechanism of a valve or an electrical breaker so that human error cannot accidentally introduce energy.
Yeah.
But for high-hazard environments, you move to double block and bleed.
Which is what, 2 valves in a drain?
Yes. Closing 2 separate valves in a piping system and opening a drain or vent valve located between them. Or, for absolute certainty, you use blinding or blanking. You insert a solid plate of engineered steel, a slip line, into the flange and bolt it tight. It physically severs the pipeline. Absolutely nothing can get through.
Then you have purging and flushing.
Right. Purging involves flowing an inert gas, like nitrogen, through the equipment to sweep out hazardous vapors and displace oxygen. By removing the oxygen, you break the fire triangle. Alternatively, you can use continuous forced air ventilation to physically dilute hazardous vapors. These are physical, measurable controls.
And the person legally responsible for verifying those claims under OSHA 1910.146 is the entry supervisor. They cannot just sign the paper. They must physically verify tests are conducted, rescue services are available, and terminate the permit immediately if a prohibited condition arises. But skipping steps turns permits into lethal illusions.
It really does. Look at the Didion Milling combustible dust explosion in 2017 as a parallel for management system failures. While not hot work, it perfectly illustrates normalizing deviance.
Oh, right, the corn dust.
Yes. Management treated smoldering fires as normal and relied on a food safety master sanitation program to handle explosive process dust. Administrative paperwork existed, but it was the wrong physical control for the hazard.
Okay, let's unpack this. If I'm a worker and my supervisor hands me a signed permit, human nature says the boss says it's safe. How do we break that blind trust in the paperwork?
Breaking that trust requires visible, active, ongoing physical safety measures, the most crucial of which is having someone whose sole job is to watch for fire.
The fire watch. And let me just say, fire watch is not a spectator with an extinguisher.
That is a fundamental distinction.
Sure.
OSHA Standard 1910.252 thoroughly outlines the requirements. The 35-foot rule is central here. All combustible materials must be relocated at least 35 feet from the worksite in all directions or protected by flame-proof covers.
Because sparks ricochet.
Exactly. And the fire watch must be highly trained, equipped, and familiar with alarms. They must remain on duty for at least a half hour after the hot work is completed.
To watch for smoldering fires.
Yes. A piece of hot slag can initiate pyrolysis in a crack in a wall, slowly baking for 30 minutes before reaching auto-ignition temperature. Also, ducts and conveyor systems can transport sparks far beyond that 35-foot radius. A spark from a grinder can enter a dust collection system and travel hundreds of feet through ductwork.
But here's a massive vulnerability. A facility might have great fire watch rules for its own employees, but what happens when they were an outsider? This leads to the massive gap in contractor safety, the contractor chasm.
Host employers bear significant responsibility for the safety of outside contractors. They must inform contractors of site-specific hazards, coordinate operations, and conduct post-job debriefings. The facility owns the hazard. Therefore, they own the absolute responsibility to communicate it.
And contractors must obtain permits, understand materials, and follow LTO. We saw this disintegrate at Partridge Raleigh. The string of failures was wild. The contractor company provided zero hot work safety training. The host facility had no safety requirements. 3 contractors died because they not only did the lit torch test, but failed to realize an adjacent tank was venting crude oil vapors right into their sparks.
We saw it at MR Oil in 2008 as well. 2 contract workers killed welding above crude oil tanks. The host company had zero formal programs to select or oversee contractors.
This sounds like handing a stranger the keys to your house, asking them to fix the roof, but forgetting to tell them the stairs are rotten and the basement is full of fireworks. If you own the site, you own the hazard communication.
I agree completely. And these failures stem from deeply ingrained myths about industrial safety. Let's bust them right now.
Welcome to our Myth versus Reality segment. I will tee up the myth, and you destroy them using the OSHA and CSB data. Myth 1, empty means safe.
Reality. Empty tanks have a headspace filled with residual sludge and vapors. This trapped gas makes them explosive. Empty does not mean vapor-free.
Myth 2, if we test the gas in the morning, we are good for the day.
Reality. Solar heating and microbial action change the atmosphere hourly. Continuous monitoring is absolutely required.
Myth 3, a signed permit guarantees a safe worksite.
Reality. A permit is administrative. Safe work sites require physical controls like blinding, continuous ventilation, and active supervision.
Myth 4, if I don't see a hazard, there isn't one.
Reality. Methanol vapors like a Bethune Point and hydrogen gas like a PCA are completely invisible. The first visible sign of a hazard is often the explosion itself.
Man, that is a heavy reality. Let's move into a segment we call 5 sentences that should stop a hot work job. We'll take turns dropping these massive red flags based on the source text. Number 1, we already tested the air this morning, so we don't need to check it again.
That's the Meduva and TEP-PPO failure in real time. Number 2, it's an empty tank, we're good to go. This is the headspace vapor trap we discussed.
Number 3, just use the torch to see if it flashes. The fatal Partridge-Raleigh method, literally the most insane thing I've read.
Number 4, they're just contractors, they know what they're doing. This is the MAR oil oversight failure. You have to communicate hazards.
And number 5, the permit is signed, let's just get this over with, the ultimate administrative trap. So, practically speaking, what do? Let's get into the before you strike the arc segment. A practical checklist based on the CSB's 7 key lessons. Lesson 1, use alternatives.
The safest hot work is no hot work. Can we use cold cutting or hydraulic cutting?
Lesson 2, analyze the hazards. Formal hazard assessment, or JSA, before anything starts.
Lesson 3, monitor the atmosphere. Use calibrated combustible gas detectors continuously.
Lesson 4, test the area. Don't just test the tank. Drain, purge, and test all surrounding tanks, adjacent spaces, and interconnecting pipes.
Lesson 5, use written permits. Qualified personnel must review and explicitly authorize precautions.
Lesson 6, train thoroughly. Ensure everyone knows the hazards of the specific tanks and materials.
And Lesson 7, supervise contractors. Active oversight and hazard communication from the host employer.
So for the listener, if you're a worker, don't trust the paper. Demand to see the gas monitor. For supervisors, be an active entry supervisor. Verify the physical controls. For permit issuers, go look at the site before signing. And for managers, build a culture of process safety, not just food sanitation like Didion. Stop treating smoldering fires as normal.
Ultimately, the final thought I want to leave you with is this. The next time you look at a routine job, ask yourself, am I relying on the physics of safety or just the comfort of paperwork? Because the spark doesn't care about the signature on the permit.
We want to hear from you. Drop down into the comments right now and tell us, what is the weakest part of hot work control? Gas testing, isolation, fire watch, supervision, or permit approval? All the technical courses related to hot work and confined spaces are linked in the video description. If this deep dive made you rethink your next shift, hit that like button, share this with your crew to keep them safe, and subscribe to Key Safety Talk so you never miss a critical breakdown. Until next time, keep questioning, keep verifying, and stay safe out there.